This is a very brief introduction to solutions in water or aqueous solutions. Some terminology. Solutions. Solution is homogeneous mixture in which two or more components mix freely. Solvent is the component present in the largest amount. In our case, almost always we'll have water as a solvent, so solutions are aqueous. Solute is the substance that dissolved in that solvent. Solution is named by the solute. Solution of sodium chloride in water, aqueous solution of sodium chloride. Solution of sugar in water, aqueous solution of sucrose. Concentration is measure of solute to solvent ratio describing composition of the mixture. We may say molarity, we may say grams per liter of solvent, we may say grams per kilogram of solution or other measurement. Now, water, H2O, molecule that has 2 hydrogen atoms and 1 oxygen atoms, and geometry of this molecule is band. So 2 hydrogens are located at angle of around 106 degrees between each other, and distance between proton and oxygen nucleus is slightly less than 1 angstrom. Hydrogens in water molecules are slightly positive charged. That means electron density or charge density is located mainly in vicinity of oxygen atom and to lesser extent in vicinity of hydrogen atom. It does not mean that all electrons are removed from hydrogens. You can plot it in different ways. So this red is negative, this green is positive, or you can see that electron density is here and to lesser extent around hydrogens. You can make more detailed plot if you are familiar with concept with lone pairs. You can see 2 lone pairs here, but they are not separated. You have one cloud of electron density around oxygen atom. Because of this charge distribution, we have small negative charge in vicinity of oxygen and 2 small positive charges in vicinity of hydrogen. Of course, negative is twice larger than positive because of electron neutrality of the system. So in solid state, water molecules will be organized in such a fashion. Positive will look towards negative because of electrostatic attraction. The good assembly unit will have hexagonal symmetry. This is familiar with hexagonal symmetry of snowflakes. So this would be our hexagonal ice, usual ice we have in nature, and that's why snowflakes again are hexagonal. If we look closer, both in ice and in liquid water, we have hydrogen bonds. That is interaction between oxygen and oxygen atom through hydrogen atom that has positive charge. Delta minus and delta plus have electrostatic to each other. 2 hydrogens are looking in this direction, and hydrogens of other molecules are looking towards lone pairs of oxygen atoms. This position can be easily interchanged. Hydrogens can easily jump from one place to another because they are relatively light. Liquid water, we would not see much of hexagonal motif, but we will still see system of hydrogen bonds that keep it together and make it liquid at ambient temperature, which is unusual for such a small molecule. Say natural gas, methane, it has same, very similar molecular weight, but it is gas, and water evaporates only at 100 Celsius, much higher temperatures than any other similar compound of such very small molecular mass. Now, how compounds are dissolved in water? Ionic compounds can be dissolved because water molecules arrange themselves around ions and dissociate them from the lattice, so there is no solid particles in solution. Separated ions are hydrated, and if compound is ionic, they conduct electricity, which act as electrolytes. Now, polyatomic ions remain intact in dissociation process. So if you have sulfate in your crystal, it will still be sulfate in solution. If you have carbonate in your crystal, you'll have carbonate in solution, and so on. Let's look what happens when sodium chloride dissolves in water. You have a crystal with solid positive sodium ions and negative chloride ions, which are jumping into water, being surrounded by water molecules, and this is true for both sodium and chloride. Very primitive scheme is on this cartoon. Chloride is negative, so it will be attracted by hydrogens of water molecule, making hydrogen bond that is enhanced by interaction with negative chloride ion and positive hydrogen ion. Sodium, at other part, is positive, so it will interact with negative area of water molecule, which is lone pair area. Here, hydrogens will look outside of this assembly. This will be approximately octahedral, but the geometry of such assembly is never stable. Water molecules will jump away from sodium and come back because we talk about liquid. Same is true here. So this is just a cartoon, but it's very helpful to understand the interaction between ion and water. Hydrogen bonds exist not only in water molecules, but also in different other molecules that has OH and NH groups. So in this case, in ethanol, hydrogen atom of OH group can make hydrogen bond with oxygen atom of another ethanol molecule. Still the same positive charge on hydrogen, negative charge on oxygen. Larger compounds of molecular nature dissolved in same manner. Solute particles are surrounded by water molecules. These molecules are not dissociated. So if you look at sucrose, common sugar, has lots of OH groups and have several oxygen atoms, in a cycle here and here. The interaction will be hydrogen atoms of water will be attracted by oxygen atoms of sugar, and oxygen atoms of water will be attracted by hydrogen atoms of hydroxy group of sugar molecule. So we have plenty of water-sugar interaction, and little surprise, sugar, as you well know, is fantastically well soluble in water, despite being a relatively heavy molecule.